graph of f have a horizontal tangent,
Oh yeah.
and then use n as your integer variable. So it's the whole like 2 pi over 3 plus 2 pi n kind of equation.
So what's the equation? Sorry.
It's f of x equals x plus 2 sine x.
I like. Oh, this is beautiful. I love this problem. You would, Jeff. All right. So by now we have to know what the hell horizontal tangent line means. What's that mean?
0. What's that 0?
0.
Where f of x equals 0.
No.
Or where the derivative of it.
Yes. 0 slope, which means what? Calculus computationally.
Derivative.
Derivative, set it equal to 0. Kick x. I like it. So what's the derivative of this? I'll do this one. Yay. Thanks, Jeff. Is that all right? What's the derivative of this? 2 cosine. I like it. What was it about trig functions? Which ones come out negative? The co stuff. Cotangent comes out negative. Cosecant comes out negative. Cosine comes out negative. That's kind of awesome. And like, for example, what's the derivative of tangent? Somebody, hopefully. Derivative of tangent. Secant squared. No. Remember, what's the only trig stuff that comes out negative? Co stuff. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. That's awesome.
Are we going to have to, I mean, what's the
You have to know those, yeah.
Yeah, you have to memorize them, right?
Yeah, so what's one good way? Co stuff is negative. That's good to know. There's an analogy between stuff like tangent, secant squared, cotangent, cosecant squared, negative, right? You kind of with me? What about derivative of secant's a little weird. Derivative of secant is secant x tangent x. So derivative of cosecant is negative cosecant x cotangent x. I mean, yeah, that's a lot of ways to memorize shit, right? So I don't know what else to do for you if you can't get that one. What's this guy then?
2 plus cosine x.
Kick ass. And then what do I want to do with this? Set it equal to 0. Yeah. And now you're back in trig or pre-calculus. How do you solve that equation?
Subtract 1 divided by 2.
Yeah, so you end up with cosine x. The output has to be negative 1/2.
Right.
So now you got to figure out which angles that happens at.
Okay. But then, where I get stuck is the adding the 2 pi n or, the pi
All right.
n.
So that's the pre-calc stuff. I mean,
Yeah.
that's what's the period of sine and cosine?
Period. Negative pi over 2 and 2.
No.
Or pi over 2 and pi over 2.
No. What's the
Oh,
period?
2 pi.
Yes. Cool. So then, whatever happens again 2 pi later, or 2 pi before. So the fundamental answer to this question is what? What's the base answer? And then you add, subtract 2 pi k or 2 pi n, whatever your teacher liked better. Does this sound vaguely familiar? So what's the basic answer? What's the fundamental stuff? And then you got to do plus other shit.
2 pi over 3. Right?
Yeah, since we're down, we got to be negative, so we got to be in the second quadrant, and then 6 degrees of pi over 3 is where cosine's going to be smaller. Kick ass. So 2 pi over 3 plus 2 pi. Yeah. Right. Now, where else does it happen, though? What's the other answer? Is there another place where this happens? Yeah. So then 4 pi over 3 plus 2 pi.
I guess I'm just confused about can you say again how to think about it?
Yeah. So if it happens here, it has to happen again 2 pi later, because it's the same place, right? If I add a complete revolution, I end up where I was. I'm facing right there, facing you. Let me turn all the way around. I'm facing you. Oh my God. Right. So when I add 2 pi k, I'm just going to twist around a full revolution, or backwards. Could be
So what's
negative.
the mentality of knowing that I need to add 2 pi k? Like, why do I know that?
Because cosine and sine look like that. So if it's at this level, it's at this level, it's at this level.
Okay,
An
so it's
infinite
every
number of times.
period.
Yeah. unless they give me some restricted interval over which they want the answers. So remember when they used to say 0 to 2 pi? So then I didn't have to do all that shit. I would just have to say this and this. But if they just are like, find all the places, well, where is it going to have a horizontal tangent line? A lot of places, right? Maybe.
How do you, so then what's the designation of the just pi n? Like the 2 pi n, or the...
That represents however many turns you want to make.
Like the 180, right?
360.
Just the pi. No, because some of the equations are just pi.
Because what trig functions have a period of pi? Sine and cosine have a period of 2 pi.
Right.
Because they live between without any transformations, they live between 0 and 2 pi, right? And then you just repeat that shape. That's a wavelength. What lives? Yes, tangent lives from negative pi over 2 to pi over 2. How long is that? Pi. So its period is pi. So you're going to have, like, for a lot of tangents, you're going to have plus pi k, or, right? I like it. Now, I'm not going to reteach this, but, I mean, why can't I capture both of these in one statement? Because these are not the same distance apart as these are. If I had one answer was here and the other answer is right there, then I don't have to do 1 plus 2 pi and the other one plus, I can just do 1 plus pi k, because then it'll just bounce between the two because of the same distance on either side. These weren't. Shit, I need 2 separate statements. Oh God, okay. I love it. So I'm not saying, it should be on the tips of your fingers, but it's got to be able to kind of creep back. Oh yeah, I remember this. And drawing yourself pictures, my God. Whenever you deal with trig stuff, you should have pictures in most of the problems. They don't have to be beautiful either. They just have to be a little, look at that shit, that's not beautiful. That's not no scale or shit, who cares? I just need a little anchor, a little visual anchor. All right, so anything else from homework stuff? Yes. $50. 2 point who to what? 2.8. Ooh, yeah, I like it. All right, so 50. How to use this here? I'm going to try to regraph this one. There it is. So this is the one that gives you multiple colored graphs. And one is F, one is F prime, one is F double prime, one is F triple prime. They look polynomial in nature. I don't know if you guys, this is number 50 in section 2.8. You don't have a book. So if I said, if I only put 2 things, obviously it's going to be easier. But which one is the slope of the other one? Let me make it a different color. So here's one of them, and here's the other one. Which one looks like it's the slope of the other one? The purple one is the slope of this one because this is squared and this is cubed. And we now know for damn sure that the degree goes down by 1 as you take derivatives. But what sucks is you could be wrong, to be honest. Because maybe this is x to the 4th. And the derivative of that would be x cubed. So they give me more graphs, so that actually kind of helps, believe it or not. Oh wait, I just need to turn you on now. Pop. Okay. So, one thing I always look for when I'm trying to think about who's somebody else's derivative, one thing I could look for is who goes through 0 when the other one has a flat point. That's good evidence that that first one is the slope of the other one. That's one thing to look for. Well, I'll put it on the mouse too. This one here, right? The mouse just couldn't take it anymore. So one of these is F, one of these is F prime. So one thing to notice is, like this guy, just to show you a couple examples. This guy goes through 0 here, and what's happening on this curve at those points also? Right? And does this curve have any more places where it's a horizontal tangent line? No, right? So, I mean, are you supposed to be able to look at this and tell the answer within 10 seconds? Oh, shit, no. I have just started. In fact, what I'm going to do is I'm going to figure out which looks to be the slope of another one, but then I got to start building off of that too, because they have to identify all of them. So just because I know maybe this guy, its derivative is this guy, maybe, but I don't know where it is in the order of derivatives yet. So that's a possibility, right? So what's the simplest one? Looks to be this guy, right? What this guy right here, is that an x squared? Why? How do you know that's not an x squared? It looks parabolic to me. I'm not saying you're wrong. In fact, you are very right. But what is it? What's the feature of this guy that tells me it's not just an x squared? It's flatter. I like it. In fact, x to the 100th power, if you graph that on your calculator, it's going to look like this. Because 0.8 to the 100th power is basically 0. 0.9 to the 100th power is really close to 0. So it's like almost 0. And then what's 1 to the 100th power? 1! Holy shit. And what's 2 to the goodbye? So it looks more like a U. So the closer this looks more like a U, like a, I don't want to say not a U, but a this. It's not really one of our letters, but like a flat-based U. The flatter the base, the higher the power. So I'm doing a couple things at once here. I'm looking for where is there a horizontal tangent line, and is there another function that goes through 0 there? So this guy would have a horizontal tangent line right there. That graph goes through 0 there. Right? I like it. Now, the other thing is, the slope is positive, then it's negative, and then it's positive again. Right? So that matches too. Okay, maybe. But I'm also using the fact that something that looks like this should become something that looks like that. If this is x to the 4th, that should be x cubed, so forth. Right? I'm also using the shape of them to help. Does that help start to tease that apart? That's not going to be a quick problem, is it? It isn't. It shouldn't be. Is that enough to get you going? Who asked that question? I can't remember. Is that enough to get you going? Okay. Because sometimes it's like, I don't even know what the hell. They didn't even tell me what F or anything. Shit. That's all I want to say about that, because that's a really good problem for you to really tease out. Okay. Anything else from homework? Over. Done. Oh well, everybody missed that. People at home. Try and come in here once. Yeah. All right, nothing else from homework? Everything else good? Okay, all right. So let's kind of review what we did last time and then get into this funky chain rule business. Product and quotient rule. Now to use the product rule on this. What's the product rule say? It's a little too warm now, right? So it's just come on, dude. Turn it off. Done good stuff. Now stop. What's the product rule say? Sweet. What is mine say?
Times the derivative of the second function.
Yeah, so each one gets a turn. You don't do both at the same time. We did an example where assuming that's the way it worked led to bullshit. So that couldn't be the way it works. And then we proved using limit definition how it really works. We proved it. So to do this derivative, I do the derivative of one, leave the other one alone, plus leave the first one alone, derivative of the other one. Did I actually take any derivatives yet? No, I just wrote the rule down so my brain can handle all the multiple shit I gotta do. If you want to be mean to yourself and try to do it all at once, it's your choice. So now what is the derivative of x to the 1/2?
X to the negative 1/2.
Yeah, let that be nice. Plus x to the 1/2, derivative of this guy.
3x squared minus y.
Kick ass. And then you can distribute. Now obviously if I were you, I'd say I would have just distributed first, but again, today with chain rule, we are finally going to unlock the true power of product rule. Because I completely agree with you. It's freaking lame by itself. It just is. Poor little thing. It just is. So now, I don't know. I don't care about the rest of this shit. Just bring that through, get your like terms together. Quotient rule is the one that's a little bit freakier. So let's take a look at a quotient rule example.
Quick question on this before you erase it. A lot of the problems like this end up turning back into like 1 over x square root of x, right? Like where it says 1/2 x to the negative 1/2. And then later, like maybe the next step would be to rewrite it as 1/2 1 over the square root of x.
Sure, maybe. In
So-
this case, not really. On this specific
Well, and
problem.
that's what I'm wondering, like when do you know when to convert it to...
Well, here, why do I know I'm not going to do that? Because that's just extra work. Because what do I really want to do? I want to distribute. And what's going to happen to the powers once I distribute it? It's going to become positive.
Okay.
So I'm not going to put anything down because the minute I distribute, I got nothing negative left. Does that make sense? I mean, thinking ahead to what I've got to do next informs you how you want to write it. Yeah. So what I'm going to do next here, distribute. I like it. Now, to be honest, let me do another problem. If the problem was very simple, like, now how do I want to do this? I love this problem. You would, Jeff. Before I start taking derivatives, what do I want to do with this? Rewrite it. It's not in a good form. It's not in a form that matches the rule. How do I rewrite this? I have a special place in my heart for the people that write a 3. How the hell did that get up here? Get out of there, you stupid thing. 1/3. Now, how do I rewrite 1 over the square root of x? That's x to the negative 1/2. 1/2 because it's square root, negative because it's on the bottom. So when you bring it up, it's unhappy. Whatever works, right? I want to be down there. I'm not happy. Okay. Now I can attack it with the rule. So what's the derivative of this going to be? Negative 1/6, because there's a 1/3 there already. X to the... Good. And inherent in this problem, now if you stop there, I'm not going to really take points off, but this is what you're talking about. Since it started off like this, it should really end up in radical form, so what would this look like now? What's going to be in the top?
Just 1.
Negative 1. And then there's a 6, and then there's a square root of...
Or to 3.
Yeah, the negative brought it down.
Yeah.
Yeah. And then this you can do shit with, but I don't care. Again, I would do more with that if I had to do something else next, but if the question is just find a slope, all right, I'm done. Okay, I like it. So that wasn't product or quotient, it was just a little side note. So let's try quotient rule out. Right in the middle of the board. So we got this here? Everybody's neutral. I like it. I'm Switzerland. So if I have, in general, what's this rule say? Let me write it differently than I did before, just to be evil. Because the rule doesn't give a shit what's in there. So what would the F prime be in this? What's the rule say?
Top first.
Top, I love it. Top first. If you like the Heidi Lodi bullshit, that's fine. That's fine. I have nothing really against it.
It's Lodi high, Heidi low.
See, as a student, it makes sense both ways. So the more I understand the idea, the less I need songs and I need mnemonic devices. I'm not saying there's not a place for music in math. I'm not saying that. But I'm saying those kind of things make it seem like math is harder than it is. Because you're like, oh, if I didn't have that, what would I do? Well, you just understand the idea, maybe. And everything will be fine. So it's this, and then what goes here? Minus, why? Because what am I going to do here? G of x h prime, right? Where's h? So when I do its derivative, it's a negative's going to come down. That's why there's a minus in this rule. I love it. I don't need no song to help me remember this shit, because I understand the idea. I know. I rant and rave about things. And what goes on the bottom? H of x, I like it. Square, kick ass. If you look at the book, it's going to have an F and a G and a G down here. Who cares what letters I put there? The rule doesn't give a shit. Right. I like it. So, if I have this problem, let me put it over here. What you got, John? Oh, let me do this. Don't put that down. Erase that. Yeah, buddy. So let's attack this. So the derivative, there's nothing I can do to simplify. There's no identities I want to use. My God. So how do I do this then? Derivative of what? First. No. What's the song? What's the top first? Right. So do the derivative of 2 sine x plus 1 first times the bottom. Minus, because one of them's on the bottom. Now you leave the top alone times the derivative of the bottom. So that's that idea I talked about earlier. Almost every rule we do, it's going to have a place where everybody gets their own term. What's up, Shane? You all right? What's up? Go ahead.
Why do we do the minus again?
Say again?
Why do we do the minus again?
So when we first did these, now watch. Can't I write this as g of x times h of x to the negative 1? So when I take this guy's derivative, wouldn't the minus come down? There, all right, that's it. That's why. That's why. In fact, I think I told you that I never did quotient rule. I always just brought the thing up and did product rule all the time. That did make a few things harder than it should have been, but I just really hated quotient rule because I didn't like the way they taught it. It didn't make sense to me. Anyway, all right. So you could. That's really why there's a minus sign, because it would have a negative power on it, and that negative would come down. That's why. So everybody cool with this so far? What's up?
Well, what am I missing? Because the denominator is supposed to come up first, times the derivative of the numerator.
What's 2 times 4?
Or is it the derivative of the denominator?
What's 2 times 4?
Okay, 8.
What's 4 times 2?
8.
Okay. So it gives a shit which one of these I put first.
Okay.
Right. So that's the other thing the song makes you feel like. The song lyrics say this goes and gives a crap.
Well, so does the rule, actually.
No.
Well, it is written, that is the rule. So that's why I'm trying to remember it the by the book, you know what I mean? Because this is confusing when you switch it.
Oh, all right. Gotta let go of that shit.
Especially when you're subtracting, like it especially has to be in the right place.
Well, obviously, that's why my rule, my song is top first. What do I mean by that? The top gets the derivative done first. That's what I mean by that.
But it is, in fact, different than the written rule. The written rule is the denominator
Yeah.
first
Yeah.
times the derivative of the numerator.
I just so don't give a shit.
I know.
Anytime I see A times B, it's the same as B times A.
Yeah, I get that.
Yeah.
I get that.
Yeah.
But fine.
Okay, but if
I'm
you
not gonna
write
argue it. It's
no,
fine.
no, no. If you write it that way, you'll be fine because of this.
Mhm.
It's all good. And then what goes here? The rear of the bottom. I like it. And on the bottom goes. Yeah, bottom guy square. I like it. Go ahead and finish that out. Yeah, they sure did. Okay. All right, let's see. So what do we get? We get 2 cosine x times 2 cos x minus 1 minus, well, that's going to become something interesting, because what is the root of this?
Negative sign.
Good, so it'll be plus 2 sine x times this, all over this business. And yes, I know I've said this before, but there's no way in shit that this can reduce. Because you can't use division to break into an addition, right? It's like Watergate level shit. Yes?
I have a question. Why in the 2 cosine x minus 1, for example, when you take the derivative of it, the minus 1 stays? Just considering...
It doesn't? What do you mean? Where?
No. Like, if the 2 cosine x minus 1,
Yeah.
when you take the derivative of that, just in
Yes.
general, like by itself, pretend
Yes.
that rest of the problem doesn't exist.
Sure.
It's 2 negative cosine x minus 1, correct?
No, what?
Or
So
does the 1 go away?
Of course, yeah. Just like the 1 went away here, and the 1 did go away here, too. Yeah.
Okay.
Yeah. Why? Because what's the derivative of any constant?
Yeah, I know, but I thought that I've seen some problems where it stays and it confused me, so that's fine. If it's supposed to disappear,
You gotta show me if you see one of those. That's a huge typo, if that's true.
okay.
But there might be other shit happening around. I don't know. So let's see. What can I do next to start to simplify this? Obviously, I do what? Distribute. Yeah, so I get 4 cosine squared x minus 2 cos x plus 4 sine squared x plus 2 sine x all over cosine x, what was it? 2 cosine x minus 1 squared. So what's really nice on the top? At least I thought it was nice. I don't know.
You can factor out
No factoring. What's cosine squared plus sine squared? What's cosine squared plus sine squared? 1. So it's a couple cosine squares plus a couple sine squares. 2. So what's 4 cosine squares plus 4 sine squares? 4, okay. And then I stop. That's enough. Yeah. It's not going to go anywhere. Can't factor the top because it's not quadratic. You guys all right with that? What's up? I mean, if you leave shit like this in there, you will lose points. That's, you know, your most basic trig identity. I know there's an extra factor 4, but you factor that 4. Maybe that's what you're going to say. Factor 4 out if you want to look at it like that. So let me ask you this, a little side note. Is everybody cool with that? That's f prime. I could ask you a question like, find the tangent line to this function at the point pi over 2 or something, right? I could ask you that. I told you I would ask you that question a few times. I could. I'm not going to. What's 7 sine squared x plus 5 cosine squared x? Yes, you got a couple extras too. 5 plus, because you got 5 sine squares plus 5 cosine squares is 5, plus the extra 2 freaking little sine squares you had running around. Okay, right? That's how you really use those trig identities. You don't let coefficients bother you. You just have to have enough of each to go together to complete the identity. That's all. I like it. Okay. There is one little thing, I always forget where the book puts this. Oh, shit, everybody have this? I don't know if you guys have run into this yet in your homework. Nobody's asked, so I'm concerned now, but if I have something to the x, right, and let me be more specific, if a is greater than 1, what does that look like? Without any scale, just the shape of it. Can you draw it in the air for me? Yes, I love it. I like it. So it's like this. Why? Right? What's this? Let's put 1 point on here. 1. I like it, because anything to the 0 power is 1. Except for 0. 0 to the 0 is indeterminate. We're going to have that one later. Yay. Let's try to sketch this guy's slope. Right? So, is the slope 0 anywhere? No. Is it approaching 0 somewhere? It's becoming, yeah, back here. It's approaching 0. And then what's it doing? So way back here at negative infinity, right? At negative infinity, it's 0. That's where this will flatten out. So basically, another way of saying it, it never flattens out. But then what happens as I move along? What's the slope doing? Getting bigger. I love it, right? So isn't that exactly what this shape is already doing? Isn't it already close to 0 and then increasing? Okay, so what's interesting is, let me stop right there. Does that make sense? If I try to graph this guy's slope, the shape of the slope will be very similar, at least, to the shape of the original function. Because the slope wants to start low, and so does the function. And then it gets bigger, bigger, positive, and so is the function. Holy shit. So this is one function whose slope at least is similar to the original. There is a number. And I'm going to cut through a lot of the crap. You can look in the book and read through the proofs and all that kind of business. But there is a number in between 2 and 3. And this is just one example of why we gave it its own symbol. Maybe you know what numbers between 2 and 3 that we gave it its own symbol. E. So here's what's really, really cool. In fact, let me do a little bit more specific stuff here. Yeah, let's do this. Let's say I have f of x equals a to the x. And I want to know what f prime is at, what do you want to say, Jeff? Let's just say what f prime is. Let's see how far we can get. Do I know what its derivative is right now? No. I really want you to understand this. Why can't I use the same rule that we use for x squared? The 2 comes down and it goes down by 1. What form does that work for? X to the n. Is that the form that this is in? Nowhere near, right? In fact, it's like the opposite. Here, the base is the variable. That's what that rule works for. Here, the base is a constant. The power is the variable. Completely different. You can't use that rule on this. No. Okay, I like it. I like it. So what would this look like? What do I have to use to investigate this guy's derivative, unfortunately? Because I don't know what the shit it is.
Table or graph?
No. No.
The definition.
Yes, the limit definition. So limit h goes to 0 of f of x plus h minus f of x all over h. All right, Green, you're not the best. Sorry. Can anybody help me with how to rewrite this? I love you guys. When you add powers, when you add the powers, when you are multiplying like bases. So this is a to the x plus h, so it must have been a to the x times a to the h. That kind of thing is going to happen in a decent number of places. So you want to make that kind of second nature. You see something to the sum of powers, you can break it up as a product. Of course you can. It's just freaking exponent rules, right? And then what can I do at the top? What comes out of the top? A to the x. And what's left? A to the h minus 1. Get out of there. All over h. What's the limit as h goes to 0 of a to the x? Yeah, it's not reactionary to h at all, right? It doesn't give a shit what h is doing, so it's just all, I'm a to the x. So the whole answer to this problem, now look, fundamentally, what do we know already about this function? It should be related very closely to itself. The derivative of this should be related to itself. So I do have it's equal to itself times whatever the shit this limit is. Yeah, Jeff. What's really kick-ass about that limit, this is the part that I've decided not to get too deep into. That limit ends up being the natural log of a. You can investigate it with tables. You can do all kinds of weird shit with it. The book does it with some tables and kind of like waves their hands. So this becomes a to the x natural log of a. Yes, sir?
Are we not bothered that the h is still in the denominator because we have the a to the x on the outside of it?
Why does it have a chance to not be does not exist? Because when you plug a 0 in, you get a 0 on the bottom and a 0 on the top, right? It's indeterminate form. So the answer doesn't have to be does not exist. In fact, it turns out to be that number, natural log of a. So for example, some concrete examples, right? I love you guys. So what's beautiful about this, we know going in, this guy's derivative should be related to itself. Bam. And then this extra shit is the little bit of an adjustment. It's not exactly equal to itself. So for example, if I had if I had this, what would its derivative be?
2 to the x natural log of 2.
Natural log of 2. Kabam. Kabam. What's special about this then? This is the most special little dude. Oh, he's an awesome little dude. What's G prime going to be? E to the x times natural log of e. What's natural log of e? 1. Yeah. So e is the base for an exponential function whose derivative is itself. So when you attack it with a derivative, it stays the same, right? That's kind of nifty. Then you start to wonder, are there other functions whose derivative is itself? No. But, yes?
I'm confused on where the natural log comes from. Can you explain that?
All right, so that's the part that I said. So if we investigated this with tables, right? If we started putting closer and closer to 0 powers in, we'll get values that are exactly equal to the natural log of that as we get closer and closer, right? Which is pretty much what the book does. Okay, I like it. And the thing that comes out of this is that this limit is exactly 1. That's why E is the one that's equal to itself. That's the limit that really they were looking at. This is part of the place where E kind of came from. Okay, like pi just started popping up everywhere. Like, we better give that sucker a symbol because it's a freaky ass number. E the same way. There's another place E comes from that I like better, but we have to learn the opposite of differentiation before we can do that. Okay, is that decent? I mean, that's the part. I'm not going to sit here and we can make tables and stuff and investigate it and show that it does look to be approaching that. Later this semester, we can actually prove that. All right, so that's a rule now in our wheelhouse, in our little bag of rules, is how to take, so again, how to take the derivative of this guy is itself times the natural log of the base. Kabam. So, for example, let's put some shit together. If I have h of x equals e to the x squared. Oh shit, that's too early for that shit. We can't do that one yet. But if I have h of x equals e to the x times 1 minus, doesn't matter, x squared, whatever, right? Or even just, why am I making it like this? Let's just make it x squared e to the x. There you go. Now product rule kind of takes on, can I simplify that? No. So then the only way I can do this is by using product rule. I can't FOIL, I can't do that shit, right? So what would the derivative of this be?
2x.
Good. Derivative of this first. You got to excuse me. I'm always going to write the rule plus. So each one gets their own term. Derivative of x squared, like you said, is 2x. And then x squared, what's the derivative of e to the x? E to the x, kick ass. And then you could factor out an x and an e to the x, right? Is that cool? Where are the horizontal tangent lines for this? What makes this 0? 0. What makes this 0? There you go. Horizontal tangent lines would be at x equals 0, x equals -2. This is factored so I can see that shit. That's why a very natural thing to do with derivatives is to try to factor it, because very often the next thing you would want to do is horizontal tangent lines. Why are they so important? Because they are the peaks and the valleys, right? What takes the least power, Johnson? This. Okay, we want to be there then. We want to use the least power. What makes the most money? This. All right, we want to be there then. We got to find out where that thing is. Okay. Whew. All right, that was a review, and then now we've got exponential functions and how the hell to do them. I like it. So now let's do the main piece of today. Today's all about chain rule, whatever time we have left. It's all about chain rule. So the first thing I want to do, like I did before, is to give you motivation as to why the chain rule should be something extra. So, for example, let me see. I made a few things up. Yeah, here's a nice one to start with. I always like to start with something very easy to look at a different way. So, obviously you can rewrite this, right? But any rule we want to use has to be able to work correctly for any way you rewrite a function. Does that make sense? Because that is the same thing as what? Equals x to the sixth, right? So whatever this guy's derivative is, this better be the same derivative whatever I do next. So if I incorrectly guess that the derivative of this should work the same way as just something to the third power, so what would happen? The 3 would come down, and then the power would go down by 1, right? This is wrong. This is wrong. This is my guess. I'm like, why should it be any different than just the basic rule? Well, because there's extra shit inside, but that's all right. So then, doing it this way, I get this. But what should the derivative be? What's the derivative of this guy?
6x for 6.
6x to the 5th. Not the same, right? Can somebody tell me actually exactly what factor this guy is missing? So I got 3x to the 4th. What factor is it missing to make it come out correct? This is not a proof, by the way, but yeah, what? 2x. And how does 2x relate to, I don't know, this guy? It's the derivative of that thing. Yeah, Jeff. So I have a function that's changing at a rate, but inside that I have another function that's changing at its own rate. So if I don't take that into account, I'm not going to get the right answer. So is it always going to be this? Yes. Do we know that yet, really? No, because maybe this was just a coincidence. Let's just try one more concrete example. Yeah, I like that. And then we'll actually prove this sucker, which is always nice. Well, which one do I want to do? I like this one. So let's say I have this function. What you got, Jeff? Yeah. What does that mean? What's another way to write that that's a little bit better computationally? This is a quick way to write it. What's another way to write this? Sorry, Albert. Right? That actually is really interesting that a lot of people don't realize that, or they don't treat it correctly. Poor little dude. So again, incorrect guess. Incorrect guess would be something like G prime, the 2 comes down, and then the power goes down by 1. So it's just 2 sine x. Now somewhere in your gut that should feel wrong because there's a sine in there. Where does that come into play, right? Does anybody know another way to write sine squared? You said it earlier. So if I write sine x, what rule that we know is true takes over? Product rule. So what do you get? You get derivative of sine is cosine times sine plus sine. What's the derivative of sine? Cosine, Jeff. Good job. So what's cosine sine plus sine cosine?
Cosine. Oh, 2 cosine.
Yeah, it doesn't matter which way, but normally it's sine first. Because cosine's an asshole, we put him at the end. Right. Makes sense on a few levels. So what factor is this guy missing to make it right, the derivative of the inside function? It's missing that link, which is part of the reason why we call it the chain rule. You can link the inside function derivatives on the end. This rule is so misapplied. And if you just do, like I say, write the rule, then do the derivatives, you will make a lot less mistakes, especially with frickin' chain rule. So let's prove chain rule. What it looks like we're saying, now let me see if you guys can see. What it looks like we're saying is the real rule should be the derivative of this, what I'm going to call the outside function. The derivative of the outside function, derivative of something squared, is twice that thing to the first power. Is that cool? Times the derivative of the inside function. So again, each one gets its own term. So let's prove this shit. So if I have a function, so how can I write this? I'm going to write it. Here's my function. That's what we're working with, something inside of another thing, right? So again, I don't know what I'm supposed to do, so what do I have to go back to? How's this guy doing? He's about to stop.